page 24 of your packet. And we're going to talk about calculating volume with something called the disk method. So our central question is, how can we adapt our knowledge of calculating volume so that we can calculate it using disks? So if we look at kind of a problem that we could have done using solids with known cross sections, let's take a look at this, where we have the base of a solid that's bound by the x-axis, the y-axis, and the parabolic relationship y equals the square root of 4 minus x. So that looks like, if we will get rid of that shape, that would be this enclosed region. And it says find the volume of the solid if its cross sections are taken perpendicular to the x-axis, or perpendicular to the red axis, and with quarter circles. So you can see this quarter circular shape. So if I create that solid here, you can see that quarter circle cross section. You can slice it, and we can see that the solid is curved on the orange exterior. It's got a flat vertical face here and a flat horizontal face here. And so we would approach this, we're building up from this flat surface, this XY plane. And we know that we need a geometric area equation. In this case, a quarter circle is 1/4 pi r squared. And our radius is that dimension along parallel to the y-axis along that flat surface. So this radius here, here's the center of our circle, here's the edge of our circle. That radius ends up being the y-coordinate of this relationship. So if that's the radius, let's square this, putting it into our geometric area formula, and then simplifying it, we can get rid of the square and the square root here, and we have an area function that looks like that. And so we know then that if we look at that slice, that we can change the location of the slice here. So we can look at that slice, and that slice goes from the y-axis here, where it's big, it's quarter circle, and then as we slice it up along the x-axis here, perpendicular to the x-axis, it goes all the way down to a circle with 0 radius at the tip there. And so we are going to then integrate them from x equals 0 to x equals 4. And when we integrate from 0 to 4, this function, pulling out the pi over 4 out front, we can actually do this by hand. So integrating this, we get 4x minus x squared over 2. And then plugging in the 4 upper bound, looks like that. And then we can plug in the lower bound, 0, subtract the 2. And this is our answer for the volume of that solid. Simplifying that would be optional. If this were a free response question, we could just read the expression like this. But I do want to compare this volume to what we're going to discuss next. So let's go ahead and, this whole thing is 0. So we'll substituting in 0 here definitely gets us 0. But we got 16 here minus 8. So we got 8 divided by 4 is 2. So we have a volume of 2 pi here for this solid. So the question is then, looking at the shape, what if we wanted to change the shape a little bit? In other words, what if we wanted to bring this shape all the way down back into the plane? So we would maybe, instead of a quarter circle, make this a half circle. And so we've dealt with semicircles before. Then you can see the symmetry there. That's just like 2 of the shapes we just had. So that volume would be twice as big, or 4 pi. But what if we wanted to go all the way around? What if we wanted to actually bring it beneath the XY plane here, swing it all the way around? Then if you notice, that cross section, that slice, so to speak, becomes a circle. And so that's what we're getting at with these notes here, is when our cross sections are disks. And of course, a disk has a circular base to it, or a circular cross section to it. So now, if instead we slice this shape, and we're slicing it again from 0 to 4, and we know that that would be 4 of the original shapes, just be 4 of these shapes. But now what we can do is, if we know that we want to slice this and have it full disks, then we can actually calculate this by taking that parabolic function, which is this black dashed line here, and actually revolving it around the x-axis completely. And so that's why these are now become solids that are formed by revolution. So let's just do a little compare and contrast here. This is our known cross sections, and we know that volume is based in the xy plane, and based in the xy plane. So we always have that flat base that we're building vertically up with, and we know the cross sections are stacked. Just like these are stacked from 0 to 4. And we know that the cross section could be a variety of shapes. So we had squares and rectangles, and we had also semicircles and triangles and stuff like that. If we form a solid by revolving a function about an axis, then we're not building the xy plane, we're revolving something. And so that if we notice that xy plane is not in the center of the shape, so it really doesn't contribute anything anymore. We have this axis that goes through the center that we have this rotation symmetry. The cross sections are still stacked though. This disk, we're going to stack that from x equals 0, which is where it is right now, to all the way out to x equals 4. So we're still stacking. It's just that all of those cross sections now, instead of being a variety of shapes, our cross sections are strictly circular. And so, what we're dealing with exclusively with this sort of method is we're dealing with a cross section that is chi-squared. And so, if we look at doing that using a revolution, then what we're saying here is we're going to set up this this parabolic relationship in the xy plane. So when x is equal to 0, y is equal to 2. When x is equal to 4, y is equal to 0. And I've got that opposite intermediate points here. Let's see, let x equal 3, and then we know y equals 1. So, and actually this parabola, I'm actually going to set it up in both the x, y, and the x negative y quadrant. And we're, of course, exclusively going to take that portion because this would not be a function. So that portion of the parabola, and we're going to work with it along the x-axis. And that's how we got that shape. So what we know is that this disk is circular. So we're going to start out with a geometric formula for a circle. And the radius is measured down from this axis of rotation out to the function. So that radius is this length of this segment here that we go from the center of the disk out to the edge. You can see the dashed line right there. And so that is the y coordinate of this function. So we're going to substitute this in for radius to get our area function with respect to x. We can simplify this. That's just y times the quantity 4 minus x. And this is our disk. And we can integrate that down from 0 to 4. And that will come up with the entire volume for this shape that has a circular cross section. So notice we're integrating the same thing as we just integrated with the first circle, right? We just had part of the 4 out here. So integrating this with 4x minus x squared over 2. We're going to go ahead and put in the 4 for the upper bound, put in the 0 for the lower bound, subtract the 2. We know this is ending, as we substitute 0 in the this will ends up being 0. And then this ends up being 16 minus 8, which is 8. So the whole value ends up being 5. And that should check. Right, when we get closer, we got 2 pi, and if you look at the shape now, you can obviously see 4 of those circle solids in this shape. Right, we've got a right and a left, and a lower right and a lower left shape. So we end up with 4 times as much. So that ends up being a really effective way instead of looking at this as a volume of known cross section like we were doing. You can look at this as a rotation, and it can simplify the math. That's the very advantageous aspect of revolutions, as long as you're not circular cross sections. So let's give this one a try now. And we're going to take a slightly different function. This is 1/2 2 minus x prime to the cube. And so this is going to be looking at the cube And why don't you go ahead and try this one on your own. So try this one on your own after we kind of lay it out for you. So we have a region bound on the x-axis and the y-axis and this cubic relationship. And we're going to revolve it about the x-axis again. And it says find the boundary division in solid. So looking at this function in the xy plane, it looks like this. So I didn't graph the whole function this time, but this will it's a minus x cubed, so it's reversed. It's going 0 at 2, so it kind of comes down like this, and then it will kind of come down like this if I graph the whole thing. But we want this and the axes proper. So this is going to be revolved along the x-axis, this y-axis. So we're going to end up with this really wide circular shape that kind of comes to a point at 2. So revolving it along the x-axis will look like this. So we can see that pointed tip that it comes to real wide at the base. You can see that circular cross section. If we back it all the way up to x equals 0, it's that big disk that has a radius of 4. And then as we take that all the way to 2, where the 0 of the function is, it comes to that shaped tip. So it looks like a disk of chocolate candy with like white sprinkles on the top. Not familiar with those things. So why don't you go ahead and pause the video and try setting this one up on your own. Okay, if you got the video unpaused, I'm guessing you're giving this a try on your own. So the first thing I would do is I would do a sketch here. So let's get some values for this function. So when x equals 0, looking at half of 8, which is 4, here. And then when x is 2, we have 0, so that's right there. And x being equal to 1 would be easy enough to prove. So 1 cubed is 1 times a half is a half, so x is equal to 1, we're at a half, so about right there. And so I can draw a smooth curve through those 3 points. And we know what it looks like when it's rotated. This is going to swing all the way over here to -4. But this sketch allows us to get our radius set up. So we are revolving on the x-axis, so we're drawing that radius from this axis of revolution out to the function, just like we did earlier. So that radius, that's the definition of that radius. We want these circular disks, these circular cross sections. And so that radius has to go from the axis of revolution out to the function, out to the edge. So that, again, is just the y coordinates. So it's this. So it's pi times this squared, which looks like that. Pi times that function squared. I'm going to clean this up a little bit. Squaring half would be a quarter. A quarter times pi is pi over 4. And then we just change the power on this. So there is our area function, and we're going to get from 0 to 2, right? That's what we're still stacking shapes, but we're just stacking circular cross sections from 0 to 2. Okay, so then the integration looks like the integral from 0 to 2 pi over 4 times pi 2 minus x to the 6th power. Okay, this is cubed, and then we square it, that gives us a 6th power. Okay, so we could do a U sub on this. This is kind of one of these things that could go either way in terms of calculator or no calculator. So I'm not quite sure that you can try this on your own. I put a pi over 4 out front, and we could do a U sub here. We could put u dt minus x, and then du dx is -1. So dx then is du divided by -1. So picturing the U sub here, I'm not going to go through all the steps, but this would be u. And so it would be u to the 6th power times du over -1. So the -1 would come out front, and u to the 6 would be u to the 7 over 7. So the integration would be u to the 7 over 7 times -1. And then, of course, we have a pi over 4 in front too, as well. And we're going to integrate from 0 to 2. So plugging in 2, and then plugging in 0 and subtracting them. And notice, so this is our answer. And this is good for a free response question. Notice this is 0. This whole thing is 0 because 2 minus 2 is 0. So this can be dropped off. So we could actually evaluate this by hand. 2 to the 7th is a bit mathematically is a bit much, but if you think about this, 2 to the 2nd is 4, so we can go to 2 to the 5th, and 2 to the 5th is 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. So we have 32 minus a negative is a positive, so we have 32 pi over 7, which is this reduced. There it is, 32 pi over 7 for that value. So you said definitely a potential here. This could also quite possibly be a calculator question as well. It's kind of dicey as to which way this level of integration would go. Okay, so let's look at the next example, example 3. It's the same function. We're just rotating about the other axis. So if you notice the same function and the coordinate axes, so x-axis, the y-axis, and this cubic, that's what we're bounded by, and now we're bounding about the y-axis. So if you notice, when we're going about the y-axis and getting this super wide shape, we're going about the y-axis, still pretty wide, but not as wide. So looking at this, remember we spun this about the x-axis. Now we're going to take this about the y-axis. So it's going to look like this. And so I've heard people refer to this as kind of like the witch's hat. So just kind of give you a visual, you can see the disc there. And so since we're going about the y-axis, this disc has a dy thickness. So we know this is going to be a dy problem. And we've dealt with, changing from horizontal to vertical axes. So we know we have a dy and a dx possibility. So if we look at the slice, we can start right here when y is equal to 0, go up to the left side, get a really wide, excuse me, a disc with a really large radius. And then we could change the disc's location all the way out to the tip of the witch's hat there, which is when y is equal to 4. So a super tiny disc there. Let me just back that up so you can see the disc a little bit better. Random location there. So let's go ahead and sketch this out again. I changed the axis of the axes a little bit. This is the x-axis. This is the y-axis. So let's go ahead and get this graphed. We know that when x is 0, we're up here at 4. We know when x is 2, we're down here at 0. Oops, there's 2. It's a little small for you to see. This is going by halvesies. So when x is equal to 1, y is equal to a half. If x is equal to 1, y is equal to a half. Right there. So there's my smooth curve. And I'm going to revolve that about the y-axis, this green axis here, to get my witch's hat. So let's set up my radius of revolution here. Here's my axis of rotation. So again, by definition, that axis of the radius is from the axis of rotation out to the function. And so that is now the x coordinate, right? When we measure out the y-axis is our x coordinate. So we have to solve this to be x equals. So I know I do this mainly in one step here. So let me walk you through it here. Multiply by 2, so we get 2y equals 2 minus x cubed. So we get the cube root of 2y. So cube root of 2y equals 2 minus x. Then we're going to bring the x over here and the cube root of 2y over there. So we know that we know this stuff. So x is equal to 2 minus the cube root of 2y. This is definitely a calculator question because we're going to have to square that, which involves foiling. That's off the table. There's no way they would expect you to do all that algebra. So our area function in terms of y is pi times the radius. You know, the radius is just the x coordinate, pi times the radius squared. So we are integrating that from 0 to 4 because we're stacking those circular cross sections starting here all the way up here. And it's pi times this squared. So grabbing our graphing calculator, then and putting that in, we're going to do a math line, and we're going to go from 0 to 4. There we go. And then we integrate, we're going to put this. So pi times, now this is the tricky part. We got to keep track of all of these brackets. These are put in automatically by the math line. I need a bracket because I need a bracket for right here. So notice my Math 9 brackets are not present in my integrand in PowerPoint. So then we have 2 minus, and now I have to do the cube root of 2y. So I like the cube root function. It's under the math, and it's right here. That's 4. And I highly recommend using it. Otherwise, we would have more brackets to introduce, and that gets messy. 2, our variable integration, our variable p is an x cube. That means y. And so we have the cube root of 2y. Now I need to put a bracket here because I got to square this whole thing. So that's what it should look like in the integrand. And then I got to complete my variable integration right there. And we get a value of, calculator, 5.026 would be an acceptable answer. 5.027 would be an acceptable answer correctly rounded. And 5.026, 54, and any other of these digits, as long as they're correct, would be an acceptable answer. You can see what I tapped here. I said 5.0265, which would be acceptable. We read the first 3 decimal places, and the first 3 decimal places correctly truncated would be 6, correctly rounded would be 7. So there's the value of example 3. So let's look at example 4 now. Example 4 is now we're rotating about an axis, but the axis is a line that's parallel to the y-axis. So we're off what we kind of call this is we're off the coordinate axis. No longer going about the green or the red, but we're going about this line, and it's actually both parallel to. Okay, so it says let the region bound by the x-axis, the line x equals pi over 2, and the function sine x. So we know sine x starts at 0 and comes up to 1. It says let's revolve that about the line pi over 2. So looking at this, we're looking at this region, okay, bounded by the x-axis pi over 2 and sine x, and we're revolving it around this line pi over 2. Okay, so this whole thing is going to rotate kind of up through the z-plane and back into the z-plane again. So rotating it looks like this. And so we've got this kind of bell-shaped solid. It's got that, that trigonometric sort of look to its exterior, flat on the bottom. And if we look at that slice starts out way down here. And slice, and it's got a really big radius, except the radius is pi over 2. Right? And so there's 5, and then it gets slowly smaller as we go to the tip. My animation is not quite working correctly, so I'm just going to move the radius right there. So we're looking at that 3-dimensional shape. So let's go ahead and get this sketched. We know that when x is equal to 0, sine of x is 0, then x is equal to pi over 2, the sine of pi over 2 is 1. 1. And then I've got 2 points in here. This one I think is about pi over 4. And we said the one was pi over 6, I think. So I just kind of guesstimated it just so that I have something in here that is clearly curved, not linear looking. Okay. And so our radius here, I'm not quite sure why this is popping up. Out of the area. Okay. Anyway, okay, so now I've got that all here. So my radius again is defined from the axis of revolution out to the function. Now this is where it gets tricky because I'm not quite sure what's up with that. Okay, this is where this gets tricky because this radius, because we're measuring it from pi over 2, its length is pi over 2 minus the x coordinate. So remember, this point right here on the function is x comma sine of x. Okay, and so this x coordinate here has to be subtracted off from pi over 2. So this is how this is set up. And this is very common this is the key to understanding revolving around a line parallel to an axis, because the radius ends up being subtracted from that parallel line. So our radius is pi over 2 minus x. Right? This is x. This whole thing is pi over 2. So the difference makes that radius. And so we need an expression for the x coordinate, which means solving this for x. So in order to solve for that for x, you have to take the inverse sine of both sides. So we end up having the radius being pi over 2 minus the inverse sine of y. So we're going to square that, put that into our area function, and that's what we're going to have to integrate. And we're going to integrate from 0 all the way up to 1. So integrate from 0 to 1, pi times pi over 2 minus the inverse sine of y times b squared. Definitely a calculator question, so let's set this up on the calculator. Let me get rid of that. There we go. Maybe that's good enough out of the way now. Okay, so math 9. That didn't work. Math 9. There we go. Come on. There we go. From 0 to 1, and we're bogging down my processor here on the math. 0 to 1. There we go. Okay, so gotta enter a pi. And this again, you gotta be careful of these brackets here. I need a bracket here, so parentheses, and then I need pi divided by 2. And then I need minus inverse sine. So minus inverse sine of x. And now just look at these brackets here. This calculator for them, so I'm close that bracket. That's just for the inverse sine of x. Now I need another bracket, because that other bracket's going to close off this whole thing, pi over 2 minus inverse sine of x. And that's important because that's what I have to square. So the square needs to be right there. Anywhere else, and you get a different answer. And then our variable integration is x. And entering that gets us an answer of 3.586. And it would be 3.586 either way, as long as it's calculated. So that is my answer. 3.586 for the volume of that side. Okay, so now we're going to look at the last example for these notes. All right, so the last example, example 5, says, what about revolving about a line parallel to the x-axis? So now we're going to revolve about this line here. It's a line y equals 4. So here's my x-axis down here. This is the area bounded by the line y equals 4 and the parabola x squared plus 4x plus 4. And it's revolved about the line y equals 4. So here is the parabola x plus 4x plus x squared plus 4x plus 4. And we're going to revolve this about the line x, or about the line y equals 4. Excuse me. So we're going to scoop this up and around, and it's going to look something like this, kind of like an M&M or a Skittle or something like that. So it's got this, circular cross section, and so let's slice it. And I'm sorry that my slicing isn't working real well right now, but we're going to have those slices going from negative 4 to 0. And it's going to be slicing if I get a perpendicular to the x-axis. Here we go. We're going to get kind of head on here. So we're going to be slicing it like this. Real tall in the center, and then show again as we go towards x equals 0. So those are going to be our limits of integration. So looking at this and setting up that parabola over here in the let's see, negative x positive y sector, so to speak. When x is 0, we know y is 4, so that's that point. When x is 2, y is 0. And then when x is negative 4, we back up at 4 again. So we have, I'm just going to put a couple immediate points in here. When x is negative 1, y value of 1, and when x is negative 3, we're also at y value of 1. So that is what we're rotating about the line y equals 4. And so our radius then is going from this axis of revolution down to the parabola. And so it looks kind of like that. And so that distance is 4 minus the y coordinate. So it's 4 minus this. And so setting this up, then we've got pi r squared, and our radius is 4 minus the function y. So using appropriate brackets here is 4 minus x squared plus 4x plus 4. So if we distribute that, then the brackets, those 4's cancel out. And then if the radius of minus x squared minus 4x, that's what we're going to have to square when we put it into the volume expression. So our area expression is pi times that squared. And our volume then, it goes from negative 4 to 0, pi times minus x squared minus 4x times squared. That should be a minus sign, not an equal sign. We correct that. I thought I had corrected that before. Here we go. So let's correct that to a minus sign. Let's go ahead and put it in that slide again. Get everything all caught up. There we go. And so looking at this, definitely a graphing calculator. Filling this out would just be messy. So doing a math 9 here. Math 9, there we go, from negative 4 to 0. 5, come on, put in 0 there. There we go. 5 times the quantity minus x squared minus 4x. So now I need another bracket here so I can square all that. Let's square that already. There we go. So we've got 5 times the radius squared, and then we need a dummy variable here, x. And so our volume is 107.233. The volume of that shape there. So these are the examples for revolving about lines about x-axis, y-axis, and lines parallel to them, the create disks. So when we get back into the classroom, we go over the takeaways and have you work on those topic questions.